Hi, my name is Patrick Lewis. I am the Director of the Technology Transition Division at Hepburn and Sons, where I lead a team in de-risking and maturing technologies for transition readiness to support our warfighters with enhanced capabilities. In this presentation, I will be discussing a small business technology transfer project that we are performing with North Carolina State University on solid-state high-frequency transformer technology. Maintenance of shipboard 60 Hz transformers becomes a costly challenge with significant schedule delays when a hull cut is necessary for replacements of such large equipment. We are developing and prototyping a hatchable solid-state transformer solution, which is flexible to serve applications from tens of kilowatts up to megawatt-class loads. Our cascaded design can be configured to interface various disparate voltages from 450 volts alternating current or 850 volts direct current transformed to medium voltage grid connections. The objective is an easily replaceable solution to minimize shipboard lifecycle maintenance and improve power density. High-frequency magnetics coupled with high-speed wide bandgap power electronic devices enables breaking up the conversion into numerous line-replaceable units and featuring system-level power density gains. Hepburn and Sons LLC provides expert advisory and engineering services as trusted advisors to the American maritime industry. The Technology Transition Division specializes in de-risking technologies for transition readiness and maturing advanced technologies to provide enhanced capabilities to our warfighters. The company was founded in 2010 and is based out of Manassas, Virginia. Here we have highlighted some of our company information, the 3 divisions of the company, and a few relevant technical projects. The Navy is seeking a maintainable alternative for 60 Hz-based medium voltage transformer rectifier serving up to multi-megawatt loads. While the purposely flexible design could serve several different applications that require an active front-end power conversion capability, the project target is the electromagnetic aircraft launch system, and we are working with NavAir PMA 251 as the acquisition program. In addition to hatchability, there are mission-specific duty cycle requirements for the input power interface as listed. Solving maintainability can come in the form of modular, line-replaceable units that are able to pass through shipboard hatches and are light enough for a 2-person carry at approximately 70 pounds or less. A modular solid-state transformer solution enables quick LRU replacements and additionally provides improved power density. Conventional shipboard 60 Hz transformers are extremely difficult to replace due to being very large and heavy. For example, a multi-megawatt application takes up to 450 cubic feet and weighs nearly 40,000 pounds. Put in perspective, that is nearly the size of a hotel room and the weight of 10 average-sized sedans combined. Our design should fit well within the comparable envelope and footprint and reduce the mass by an order of magnitude. We achieve this by using high-frequency advanced magnetics and wide bandgap power electronic devices, operating in the range of 100 kHz. The LRU design will be easily carried through shipboard hatches and could even be swapped out for replacement while operational at sea. The team is currently developing an elegant methodology to perform scaled communications and protection across the networked converter. The solid-state nature of the design will naturally add complexity. The design is set up well to implement graceful degradation as one way to address the concern of reliability. Not much will be more reliable than a conventional silicon steel 60 Hz transformer. The design approach is a networked LRU architecture. Depicted here is one LRU, including 5 cells in series to support a single phase. Each cell rectifies from AC to DC, including galvanic isolation, through the approximately 100 kHz transformer design. Each cell is estimated to achieve up to 15 kilowatts at nominally 1 kilovolt. One of the design highlights is a minimized thermal load by device packaging, board tracing, and transformer design. While accounting for mission duty cycle requirements, reducing thermal management demands can optimize for system-level power density gains. The design is also set up for operational availability due to the ability to swap LRUs at sea when needed in a plug-and-play manner. Since creating this presentation, benchtop prototypes have been built and discovery testing has been performed. The team has now successfully performed functional benchtop demonstration of 2 cells. The project is currently in the second base year of Phase 2 until August 2024. The team has conducted functional prototype testing of line replaceable unit cells, which is estimated to be at a technology readiness level of 4 as of May 2024. We are planning on using the Phase 2 option period to continue development of the technology and pursue follow-on expansion efforts. Future work includes distributed controls development, LRU packaging, a full-scale prototype validation, and land-based test site demonstration. The roadmap for solid-state transformers to be applied shipboard also involves discussion of military performance requirements standardization, commercial production partnership, and eventual Navy qualification. Presented in the table is a comparison of conventional transformer rectifier to our solid-state transformer design. The 2 most significant features of our work are the minimal corrective maintenance cost and the weight savings. When scaled to a single-digit multi-megawatt application and assumptions built in, an example system could include 180 cells assembled into 45-line replaceable units, making up a system rated for 13.8 kV AC to 1000 volt DC rectification. The baseline transformer rectifier is 40,000 pounds, while our solution could weigh less than 5,000 pounds conservatively, an order of magnitude reduction in weight. The baseline size is 450 cubic feet, while our solution could be less than 150 cubic feet. The developed solution would incorporate lower corrective maintenance costs due to the replaceable hatchability. The modularity of the design at smaller kilowatt level increments also provides form-integrated capacity of the design to meet custom power density requirements. One LRU measures approximately at 14 inches by 6 inches by 24 inches. To highlight key benefits and features one last time, our hatchable solid-state transformer solution incorporates use of modular line replaceable units that are easily replaceable and power-dense, notably compared to the mass of conventional silicon steel 60 Hz transformers. Our solution utilizes advanced magnetics and wide bandgap power electronics, featuring galvanic isolation and bidirectional power flow. The bidirectional flow capability of an active front-end converter is an especially important advantage, as that enables a great deal of flexibility and control capacity into the design, making it ideal for energy storage integration requiring charge and discharge cycles. The networked converter design is easily scalable for various voltage and power capacity requirements, which provides design interoperability. There could be wide applicability across various shipboard power system design purposes, always providing galvanic isolation. The Hepburn team is currently seeking a commercial production partner for a Phase 3 transition. During Phase 2, the team plans to continue discovery testing, validate subscale functional prototypes, develop controls design, assess the business case, and further raise the technology readiness level by pursuing scaled system development and operational demonstrations. Relevant Navy applications include integration of energy storage, interfacing combat systems, ship-to-shore connections, motor drives, and more. For commercial applications, the design could be applied to electrical vehicle charging, data center grid connection, and microgrid applications, among others. This work is being sponsored by PMA 251 within NavAir. Qualifying this technology will require involvement with the Program Office, NAVC-05, and the tech warrant holder community in pursuit of adding this solution to the qualified parts list for shipyard use. The Hepburn team is looking for a commercialization partner interested in production of this solution. As discussed previously, the technology development roadmap towards technology transition involves military performance requirement standardization, commercial production partnership, Navy qualification, and successful integration into a program of record. Hepburn & Sons LLC is located in Old Town Manassas, Virginia, less than an hour west of D.C. We are exhibiting at the 2024 Sea Airspace Expo in National Harbor at booth 1851. If you have questions about this technology or are interested in other technologies that we are de-risking for the warfighter, please stop by our booth or use the contact info shown in this slide deck to get in touch.